Hello everyone. Today in this video we will be seeing how to form a PDE by eliminating arbitrary functions. So these are the important points should be noted. The elimination of one arbitrary function from a given relation, it gives rise to first order PDE. Similarly, if we are eliminating two or more arbitrary functions from a given relation, then we'll be obtaining a PDE of second or higher order. So the logic behind doing this problem is we have to differentiate the given equation with respect to the independent variables x and y. Also, I'll be using the abbreviation AF for arbitrary functions. So let us see the first question. Eliminate the arbitrary function f from the relation z equal to f of x squared minus y squared. So from this equation, we can clearly see that there is only one arbitrary function which is f. So since the number of arbitrary function is 1, we will be obtaining a PDE of first order. Now the first step in this question is we have to differentiate the given relation with respect to x. So if you differentiate the left hand side, we'll be getting dou z divided by dou x, and differentiating right hand side, first this f will be written as f dash of x squared minus y squared, and then we have to differentiate the term inside your bracket. So differentiating x squared minus y squared with respect to x, we will be getting 2x. So we can write this as p is equal to 2x into f dash of x squared minus y squared. So this will be the first equation. And next one, we are going to differentiate the given relation z equal to f into x squared minus y squared with respect to y. So the left hand side will be dou z divided by dou y, and your right hand side will be f dash of x squared minus y squared into, so note that we are differentiating this term with respect to y. So x squared will be 0, and if you differentiate minus y squared, we'll be getting minus 2y. So we can write it as q is equal to minus 2y into f dash of x squared minus y squared. So this will be our second equation. Now, in order to find the required PDE, from this equation, we can write f dash of x squared minus y squared. It is nothing but p divided by 2x. And similarly, from second equation, we can write f dash of x squared minus y squared as minus q divided by 2 into y. So since both the left hand side are equal, we can equate the right hand side also. So p divided by 2x, this will be equal to minus q divided by 2y. We can cancel this 2 on both sides. So we'll be getting py, this is equal to minus qx, or this can be written as py plus qx, this is equal to 0. So this will be our required PDE of first order. Py plus qx is equal to 0. So next question, eliminate the arbitrary function phi from the relation xyz equal to phi of x plus y plus z. So here also the arbitrary function is 5 and the count is 1. So we will be getting a PDE of first order. Now differentiating the given relation with respect to x. So note that in left hand side we are having x as well as z. So we have to use product rule. So keeping, we can take y outside, x into dou z divided by dou x plus, we will be differentiating x alone, so it will be z. This in right hand side we can write it as phi dash of x plus y plus z into, we have to differentiate the term inside the bracket, so it will be 1 plus 0 plus dou z divided by dou x. So we can write it as y into, it is xp plus z. This is equal to pi dash of x plus y plus z into 1 plus p. So now we can write this as yz plus xyp divided by 1 plus p. This is equal to pi dash of x plus y plus z. So this is the equation we will be obtaining while differentiating the given relation with respect to x. Okay. Now again, differentiating with respect to y, note that this y and z will be the variables. So we are keeping x as constant. So x into, if you keep y, if you differentiate y first, we'll be getting z, and then if you differentiate z, then it is y into dou z divided by dou y. This is equal to pi dash of x plus y plus z into, this will be 0 plus 1 plus dou z divided by dou y. So it is x into z plus y cube. This is equal to pi dash of x plus y plus z into 1 plus q. So we can write this as xz plus xy cube divided by 1 plus q equal to pi dash of x plus y plus z. So this will be our second equation. So now in order to find the required PDE, since the right hand side are same, we are going to equate the left hand side, that is yz plus xyp divided by 1 plus p will be equal to xz plus xy cube divided by 1 plus q. Now we are going to cross multiply it and we are going to take the term commonly outside. So y into z plus xp, we are bringing this 1 plus q to left hand side. So it is 1 plus q. This is equal to x into z plus y cube into 1 plus p. So this will be our required PDE. So now problem number 3, we are going to eliminate the arbitrary function f from the relation z is equal to x into f of x divided by y. So here the arbitrary function is f, only one arbitrary function. So we will be getting a PDE of first order. So differentiating this relation with respect to x. Left hand side it can be written as dou z by dou x. In right hand side, note that here also we are having x and here also we are having x. So we have to use product rule. So first let us differentiate x alone. So it will be 1 into f of x comma y. I will be writing f of x comma y alone plus x into f dash of x by y into, if we differentiate x by y, we will be getting 1 by y. So this can be written as p is equal to f of x divided by y plus x by y into f dash of x by y. So now note that, so this term f of x by y can be written as replaced with z by x from the given relation. This one. So we can write p is equal to z by x plus x by y into f dash of x by y. So now let us bring this z by x term to left hand side. So it is p minus z by x. This is equal to x by y into f dash of x by y. Let us keep this equation as it is. P minus z by x is equal to x by y f dash of x by y. Now differentiating with respect to y, we will be getting dou z divided by dou y. We have to keep x as it is because differentiating with respect to y, x will be treated as constant. into f dash of x by y. If you differentiate the x by y term inside bracket, we'll be getting x minus x divided by y square. Because, so keep x as constant. Now we are differentiating y alone. So now replacing this dou z by dou y as q, we'll be getting minus x squared by y squared f dash of x by y. Since we are having x by y and f dash of x by y in the previous equation, we are trying to bring that term in next equation also. So bring that negative sign to left hand side. So you can write it as q into y by x, and right hand side will be x by y f dash of x by y. So now in order to find the required PDE, we can observe that our right hand side is same. So we are going to equate our left hand side. P minus z by x is equal to minus qy divided by x. So this can be written as px minus z is equal to minus qy divided by x. Now we can cancel this x on both sides. So it will be px plus qy. This is equal to z. So this will be our required PDE. Px plus qy is equal to z. So next question, form a PDE by eliminating arbitrary functions f and g from the relation z equal to f of x plus ay plus g of x minus ay. So note that in this question, the arbitrary functions are f and g. So there are two arbitrary functions. So we will be getting a PDE of second order. So number of arbitrary function is 2. So it will obtain a PDE of second order. So now we are differentiating the given relation with respect to x. So I will be getting dou z by dou x. This is equal to f dash of x plus ay. And note that if we differentiate this x plus ay with respect to x, it will be 1 plus 0. So multiplying this term with 1, again we'll get this term only. Plus g dash of x minus ay. So this can be written as P is equal to f dash of x plus ay plus g dash of x minus ay. So this will be our first equation. And second equation will obtain by differentiating the given relation with respect to y. So it is dou z divided by dou y equal to f dash of x plus ay. And if we differentiate the term x plus ay with respect to y, we will be getting a plus g dash of x minus ay, and multiplying with the derivative of x minus ay will get minus a. So this can be written as q is equal to a f dash of x plus ay minus a into g dash of x minus ay. If we want, we can take the term commonly outside also, a term. Okay, this will be our second equation. And note that using these two equations alone, we cannot obtain the PDE because the PDE will be of second order. So again, we have to differentiate these equations with respect to x and y. So differentiating equation 1 with respect to x, will be getting, if we differentiate p with respect to x, we will obtain dou square z divided by dou x squared, which is equal to f double dash of x plus ay plus g double dash of x plus ay. So this term is nothing but r. R is equal to f double dash of x plus ay plus g double dash of x plus ay. This will be our next equation 3. And differentiating equation 2. Equation 2, it is nothing but q is equal to a into f dash of x plus ay minus a into g dash of x minus ay. Now differentiating this equation 2 with respect to y. So we will be getting dou square z divided by dou y square. Already one a is there. F dash, if we differentiate it again, we'll get f double dash x plus ay. Now differentiating with respect to y, we'll get one more a outside minus a into g double dash of x minus ay. This is into minus a. So we can write this term as t, and we'll be getting a square f double dash of x plus ay minus into minus will become plus. It is plus a squared g double dash of x minus ay. And let us take the term a square commonly outside. So it will be f double dash of x plus ay plus g double dash of x minus ay. So this is our next equation, equation number 4. Now in order to find the required PDE, so see this term f double dash plus g double dash, and this is what given in equation 3. F double dash plus g double dash can be replaced with r. So if we replace this term with r, our required PDE is nothing but t is equal to a square into r. So observe that this t and this r is of second order derivative. So this PDE is a second order PDE. So final PDE is t is equal to a square r. Here the arbitrary function is taken as pi of u comma v is equal to 0. Already we have seen how to form a PDE by eliminating a function f or some other function g and phi, but usually inside the bracket there will be only one function or only one term. But note that here two terms are there, u and v. That is, u is explicitly dependent on the variables u and v, phi is explicitly dependent on u and v, and u is dependent on x, y, z. Similarly, v is dependent on x, y, z. So ultimately, we can say that phi, the function phi, is dependent on the variables x, y, z implicitly. Okay. Now we are going to see how to eliminate this function phi when it is implicitly dependent on the variables x, y, and z. So we are going to differentiate phi with respect to x and y. Note that if we are differentiating phi with respect to x, so first we have to differentiate phi with respect to u, and then we are going to differentiate u with respect to x. So similarly, since another term is also there v, we are going to differentiate phi with respect to v and then v with respect to x. So this is our first equation. So similarly, differentiating with respect to y, we will be getting dou phi by dou u into dou u divided by dou y plus differentiating pi with respect to v and then differentiating v with respect to y, which is equal to 0. These are the two equations written here. Now clearly in this one, this term, this dou pi by dou pi by dou u, dou pi by and dou v are the unknown terms. We are going to eliminate these two things from the equations so that we will be getting the PDE. So in order to eliminate these two terms from the above equation, the following determinant is obtained. So the determinant is nothing but leaving the unknown terms which has to be eliminated. We are going to write all other terms. Dou u by dou x, dou v by dou x, and here dou u by dou y, and here it is dou v by dou y, which will be equal to 0. And if we expand this determinant, will be obtain our required PDE. So let us see some problems on this method. So see the question number 1. Form a PDE by eliminating the arbitrary function pi from the relation pi of x squared plus y squared plus z squared, comma xyz is equal to 0. Now we can note that this term will be u and this term will be v. So let u, it can be taken as x squared plus y squared plus z squared, and v can be taken as x, y and z. So that the given relation can be written as pi of u comma v is equal to 0. Now we already know that we have to differentiate this u1v with respect to x. So dou u divided by dou x will be 2x plus 0 plus 2z into dou z by dou x. So similarly, dou v by dou x will be, keeping y outside, it is x into dou z by dou x plus z alone. So dou u by dou x can be written as 2x plus 2zp, and dou v by dou x, it can be written as y into z plus xp. So this is what written here. And next one, differentiating u1v with respect to y. So we'll be getting dou u by dou y will be 0 plus 2y plus 2z into dou z by dou y, and dou v by dou y, it is nothing but you have to keep x outside, so it will be z plus y into dou z divided by dou y. So dou u by dou y, it can be written as 2y plus 2zq, and then dou v by dou y, it is x into z plus yq. And then we are going to substitute the obtained terms in this determinant. So I will be getting this determinant after substitution. Now we have to expand this determinant. So expanding this determinant is nothing but product of these two minus product of these two. So I will be writing, we can take 2 commonly outside, x plus zp into, so here we can take x outside, so it will be x into z plus yq. This will be minus 2 into y plus zq, and it is, or you can keep it as it is, yz plus xy p is equal to 0. Anyhow, we are going to multiply everything. So let us keep the first term also as it is. So here it is nothing but xz plus xyq. So now 2 and 2 will get cancelled. We can multiply everything inside. So it is x squared z plus x squared yq plus x z squared p plus x y z p q. And in the next term, every term will have negative sign. So minus, it is y square z, and it is minus x y square p, and then minus, it is y z squared q minus x y z p q is equal to 0. So these two terms, it will get cancelled, and from these two things, we can take z commonly outside. It can be written as x squared minus y squared, and then these two terms. Consider these two terms. Here p x is there, and here also p and x is there. So we can take px commonly outside. It can be written as z square minus y square. And similarly, from these two terms, we can take qy commonly outside, so it will be x squared minus z square is equal to 0. So this will be our required PD. Required PDE is z into x squared minus y squared plus px into z square minus y square plus qy into x squared minus z square equal to 0. So next question, form a PDE by eliminating the arbitrary function g from the relation g of y by x comma x squared plus y squared plus z squared equal to 0. So here also there are two functions u and v. So we are going to name y by x as u and x square plus y square plus z square as v. Differentiating u and v with respect to x. So dou u divided by dou x, we'll be getting, we can keep y as constant. If we differentiate 1 by x, we'll be getting minus 1 by x squared. So it is minus y by x squared. And then dou v by dou x, it is nothing but 2x plus 0 plus 2z into dou z by dou x. So dou v by dou x, it can be written as 2x plus 2zp. Next one, differentiating u and v with respect to y. So dou u divided by dou y, it is nothing but 1 by x, because 1 by x can be treated as constant. So constant into y, if you differentiate it, you'll get that constant alone. And then dou v divided by dou y, this is nothing but 0 plus 2y plus 2z into dou z divided by dou y. So dou v by dou y, it can be written as 2y plus 2zq. Now, coming to determinant condition, we know that determinant of dou u by dou x, dou v by dou x and dou u by dou y, dou v by dou y should be equal to 0. Substituting the obtained terms, this is what the determinant will be obtaining. Now, the required PDE can be obtained by expanding this determinant. So, multiplying these two and then subtracting these two. Minus y by x squared into 2y plus 2zq minus 1 by x into 2x plus 2zp will be equal to 0. So minus and minus, we can cancel this one, and similarly in all the terms we are having 2, so we can cancel 2 also in all the terms. So the remaining part will be y by x square into y plus zq and plus 1 by x into x plus zp. So now let us take LCM and then bring that x square term to right hand side. So your right hand side will be 0 always. After that, y squared plus yzq plus x squared plus it will be xzp will be equal to 0. So finally we can write this as pxz plus qyz plus x squared plus y squared will be equal to 0. This will be our required PDE. Thank you.